Okay, so this was going to be y equals 4x minus 1/2 x cubed. So let's use a table to approximate table of secant. Secant slopes. Say it that way. Use a table of secant slopes to approximate the slope of the tangent line at 2, 4. And the book will probably give you which x values to use here, but let's just think about it on our own a little bit. So all I want to do is do a table of secant slopes with Mpq values, this being P. First of all, let's think about what x values I'd want to use here. What x value? You tell me what x values to use. X being the x of the q value to go along with the p value 2, 4. Well, wouldn't the x values you want to be close to 2, getting closer and closer to 2? So how about let's do the 2.1 thing. How about 2.1, 2.01, 2.001? Said it's so easy to do these. Let's even go out one more. Okay. Let's use those for x values. All right. Now the other thing is we need to set up this Mpq equation. What is, in general, q going to be, though? I mean, this is going to be the x values I use, but if I just say the x value of the q is x, what's the y value? Well, y value is this, isn't it? 4x minus 1/2 x cubed. And so that's going to make the Mpq equation what? Difference of the y's over difference of the x's. So I take y2 minus y1. So that would be 4x minus 1/2 x cubed minus 4 over difference of the x's. X minus 2. And so that's going to be the Mpq, the value I'm going to place on my Mpq. Okay, say it again. Okay, remember it's you always do y2 minus y1 over x2. Yeah, it's using the slope. So this is y2, that's y1. That's x2. Yeah, that's what I'm using. Slope formula. Yeah, I should have written that one first of all. Okay? So yeah, put that in here for your table. I'm not going to rewrite it. Let's just go to it. All right, put that in for y1. Okay, so parentheses 4x minus 1/2 x cubed minus 4 divided by parentheses x minus 2. Then go to the table, and we're going to do 2.1, 2.01, 2.001. Negative 2.305. For 2.1, I get negative 2.03. Negative 2.003, negative 2.003 again. Yeah. And it's that displays on mine, it just says -2, but it's -2 arrow key over to. You can see the. Oh, I did that one twice, didn't I? I didn't have that. Okay. So seemingly here, what do you got? Use a table. All right, so we got our table. All right, so what is the slope of the tangent then? Looks like it's -2, doesn't it? By evidence of this table, anyway, it appears the slope of that tangent line at 2, 4 is a -2. How'd I enter this? Be sure to use parentheses. You did? Oh, were you? Okay. Let me see. Oh, you got 1.5x cubed. 0.5x cubed. Yeah, there you go. All right. Any other question, concern? All right. Let's take this one other step here. Let's check to see that we got a pretty good answer. Okay. So we're estimating the slope of this tangent to be -2. All right. What is then the equation of the tangent line at 2, 4? At, what was the point? 2, 4. Yeah, 2, 4. 2, 4 didn't sound right. Well, they'll want you to do this. I don't know if you have to do this on all of them, but let's actually get that equation of the tangent line. I now know that the slope of the tangent line is -2. So what would the actual equation of the tangent line be? I'm looking for the y equals mx plus b form of this line. And like I said, if you like the point slope form, you want to get it to this form, but if you want to use that point slope form, that's fine too. But here, we know the m is -2, so I can plug that in for m. I've got 2, 4, so I can use that to find b. One way to do it. All right, so 4 is y, x is 2, and so that's going to mean -4 plus b. So what's b? 8. B is 8. So my equation of my tangent line is y equals -2x plus 8. Is the actual equation of that tangent line. And like I said, let's go ahead and check it. Let's graph both the equation and the tangent line there. Okay, so graph this one and this one. And let's see if we have a tangent line at 2, 4 like we had hoped. Okay, so clear out y1. All right, so we'll put on y1 is going to be 4x minus 1/2 x cubed. And then y2 is going to be -2x plus 8. We should see at 2, 4 a nice little line. Here's what mine's showing up as. I think we did a pretty good job. Is that what yours came out? Looks pretty good. All right, so I think we're on the right track here with our efforts. Question? Any other question? All look okay? So far, so good. All right. Well, the matter for our consideration today. Turns out that we can do a similar thing with, believe it or not, velocity. So let's talk a little bit about velocity. Now, usually when we talk about velocity, we talk about like if I was going to estimate my speed going to Springfield, I'd say, well, I started at 4 o'clock, I got there at 5:30. What's my average speed? I usually think of in terms of average velocity, average speed. And the way I compute that is by just taking, the distance I traveled, right? Speed's distance divided by time, right? So I take the distance traveled divided by time. Average speed. Okay. All right. Well, what we're going to get to, hopefully, by a similar process of the slopes of the secant lines and tangent lines, is we're going to get to where we can actually determine an instantaneous velocity. And of course, instantaneous velocity. And just as the name suggests there, that's the velocity at any particular instant, at time 1, at time 2, because all this gives you is an average speed, an average from this time to this time. We want to be able to find the instantaneous velocity at a particular time. And we can do that through this kind of this same limiting type process, and I'll show you how you do that. But you see the difference there. This gives us average speed, which that's what we have calculated probably a few times. But with the idea of limits and calculus, we can actually do an instantaneous velocity at any particular time. Time 1, times 2, so forth. All right, so how do we do that? Let's say we've got a ball being thrown upward. Ball is thrown upward. Its height in feet after t seconds is given by y equals 100t minus 16t squared. You may know something about an equation like that. This is actually the initial velocity. And this is the gravitational constant. But anyway, that's just a little bit more information there, maybe than you need to know. But so here's the question: what is the velocity, or instantaneous velocity, at 2 seconds? Well, that's a good question, because the function just gives me height. You plug in a t value, it gives you height. So how are you going to get the velocity instantaneous, what velocity it has at 2, just from that equation? It turns out we can do it, like I said, with a little bit of the idea of limits. What we're going to start off with is an average velocity, or average speed. because that's what we know a little something about. It's distance divided by time. And so what we're going to do is, we're going towards 2 seconds. So to use this average velocity, what I have to do is I have to go, another little bit, few seconds. Maybe let's start with 3 seconds. So we'll go from 2 to 3 seconds. Then we can calculate an average velocity, and then we can think about what to do from there. Okay. All right. So how would I get this distance if I'm, say, going from 2 seconds to 3 seconds? Well, I'd find the height at 2 seconds and the height at 3 seconds and take the difference, right? So this distance is the difference of the y values. It's the difference of the heights. You with me on that? If I go from 2 seconds out to 3 seconds, to find that distance traveled, I just subtract the difference of those heights. Then I take, for the time traveled, I just do the difference of the times. 2 seconds from 3, so that'd be a difference of 1 second. So I can calculate that in different increments and set it up. However, do you notice here, does this remind you of anything in particular? Isn't that just like the slope? Isn't the difference of the heights going to be the difference of the y's? And the difference of the times, that's like the difference of the x's. We're just using t instead of x. You see what I'm saying? So this is going to be y2 minus y1 over t2 minus t1, I guess. It's the slope formula all over again. It's just in a different context. You see? All right. Well, let's set this up in a table. Let me give you 2 different scenarios here. One of the questions it asks, it gives you the time period lasting so many seconds, and then also it gives you an incremental time interval. It'll give them both ways, but here's the thing. If I want, let's say I'm going for 2 seconds, so 1 second doesn't seem like a lot, but it will once we get done. But let's just start with the time period lasting 1 second. The time interval then would be from 2 to 3. So I give it this way, like I said, because it gives it both ways, and the problems I'll have you do. So what I want to do then is calculate here my average velocity. And so I do that using this nice little formula here. All right. So I take the average velocity, so that would be y2 would be at time 3. What is the height there? And so that would be, in this case, the y2 would be the value of the height at 3 seconds. So that would be 300 minus 16 times 9. That's 300 minus 144. It's 156. And then y1 would be, this being x1, this being x2. y1 would be when it's x2, which that would be 200 minus 16 times 4. So that's 200 minus 64, which is 136. Did I do those right? 156, 136. Okay. I'm doing these all by hand, but in a moment I'll show you. We'll just plug it into the formula and let the calculator do it for us. All right. So anyway, all right. So that this average velocity will be 156 minus 136 divided by 3 minus 2. So that's 20 divided by 1, that's 20. Okay, so all that work, we get average velocity of 20. So that's what we're going to get our calculator to do. It'll do all this work for us, okay? All right, but let's bump it down. And the thing is, we want to get time periods smaller and smaller. And so that would be a smaller one would be like a half a second. So I would go from 2 to 2.5 seconds. What's the average velocity there? Well, let's cut to the chase here. Let's get an average velocity function, if you will, to plug into our calculator here. Just like we did on the slopes. So it'd be y2 minus y1. Well, here's the thing. These two really, aren't they? Aren't those locked in? Y1 and T1, those are locked in because in both of those cases, I'm going to go from time 2 seconds. I'm just going out 1 second, or just going out half a second, or about. So these two are locked in. So T1 is going to be 2, and the Y1 then, I forgot, was it 130, 136? And so the Y1 is just the height at 2 seconds, which was 136. We did that a while ago. With me on that? Okay. What's going to vary are your Y2 and T2. Of course, T2, I guess that's the one we're going to call the X, or T. I guess we can just call it T. And then the TI's just have X on it, so we'll use X instead of T's. But anyway, and then Y2 is just going to be this expression here, just like we did on the slopes. Okay? With me on all that. All right, so let's plug this into the TIs or whatever calculator it is, where we can get to a table of values. And let's see, we'll start with the top is 100t. So it's, like I said, the calculator uses x's, so I'm just going to use x. 100x minus 16x squared minus 136. Then divide that by x minus 2. And that'll plug it in where I can just do my increments as I need it. Okay? So far, so good. Question about the formula there, anything? All right, so if I go to my table, what I'm going to do then is I'm going to plug in these x2 values. Now, if it gives you the time period, you'll have to, make the adjustment. Like if I was going time period 1 and I was starting at 5 seconds, then, the x2 would be 6 and 5.5 and so forth. So you have to make, if it gives it like this, you just have to add it to your original x value there, time. These are the ones I'm going to plug in for x. This column right here. All right, so I did the 3. Let's check it though. 3, yeah, I get 20. 2.5, what do you get? What do you get? 28, yeah. 20. Okay? That's what I got. Just check it. Just making sure. Okay. All right. Okay, so let's go. We're trying to get an instantaneous velocity, a velocity right at 2. So I got closer into 2 here. So let's get a little closer. So maybe my time period only lasts 0.1. So that would go from 2 to 2.1, right? So I'd plug in my 2.1. That gives me a 34.4. Oh, these are going up, aren't they? Well, let's see what happens. Get the idea? What's next? 0.01 time period. So that would go from 2 to 2.01. It's 3584. 35.84. All right. Let's go at least one more. All right. Let's go a 0.001. That's 2 to 2.001. So let's plug that in for x there. I've already got it. I get 35.998. And then 0, 0, 0, 0, 1. Let's go one more. Why not? So 2 to 2.00001. And that gives me 35.9984. Aha. I think I'm onto something here. It appears that these velocities, these average velocities, are honing in on what? 36. So I'm pretty safe here in guessing, I think. We'll get more precise even later on, but yeah, these are going to the value of 36. So I think I can guess here that the instantaneous velocity at 2 seconds is 36. All that just coming from just knowing the height function. If I know that height function, I can figure out how fast that ball is going at any second I want to. With this process and then with others as we go along the way. But it all goes back to this. It's all tied here, what we're going to do. Okay? We just have to get certain pieces along the way. Okay?